relativity stuff?
Well, we'll first start out with, are there any questions on chapter 37? Are you about to come up with a question, Thomas?
I'm looking. I have no questions.
Okay. So we sort of left off with, well, we basically had the following formulas that time is equal to gamma times the proper time, and that the proper length is equal to gamma times the length. And remember that proper refers to the, just call it the non-moving frame. So in the case of Earth rocket traveling to planet X, this is from Earth's point of view, E's point of view. That the time that takes place in the ship here is not proper time because the rocket is moving relative to Earth. However, the distance to the planet is in the proper frame because it's not moving relative to Earth. And then from the rocket's point of view, Earth is zipping back this way, planet X is zipping towards it. The time for X to get to the rocket ship is the proper time because they're measuring the time of the rocket. The people in the rocket are measuring that time, so that time is at rest relative to, rest frame. That was the word I was looking for earlier. So here, proper time is in the rocket because they're sitting there watching this thing happen, and that time is relative to them. And here the length is proper. But in either case, this is the rocket frame, and this is Earth in this scenario. So this brings in the question of at least the first glimpse at how fast does an 11-foot car need to travel to fit inside a 10-foot garage. And so whenever you're faced with a problem like this, well, you know gamma's going to come into it. do the quick review of what gamma is. It's 1 over the square root of 1 minus beta squared. And beta is just how fast an object is going divided by the speed of light.
But isn't that in metric as opposed to, that's in metric as opposed to imperial?
No, I mean, the formula holds true regardless of what unit system you're using.
Oh,
We tend to hang out in the metric world, but partly because the speed of light's relatively simple. C is approximately equal to 3 times 10 to the 8th meters per second. 2.99 something, 2.98 something. Yeah, so these equations hold true regardless of the unit system you're using. Because I could make it 10 meters, 11 meters and 10 meters, and, well, an 11 meter long car would be awfully big.
yeah.
A stretch limousine.
Yeah.
All right, so what is the smallest value gamma can be?
I know it can't be 1. Well, no, wait, no, it can be 0, sorry. It can't be divided by 0.
I think you're mixing up beta and gamma. Gamma is looks like the fish died.
Yeah. I was looking at the second equation if beta was.
The smallest it could be?
Yeah. So we take from another point of view, what's the smallest, actually, what's the smallest beta can be?
I think I'm down and getting confused between smallest and largest.
So as I open it up, what are the limits of beta?
Well, beta can't be 1, so anything below 1 would work.
Okay, and the smallest beta can be?
-10.
Whoa, how'd you get that?
Cause there's no limit on how small it could be.
What's the lowest speed you can have?
0.
Yeah,
And look at the speed, you're just going backwards.
speed doesn't care about direction.
Okay.
So beta can't, if it's equal to 1, you're a massless particle according to according to the theories. But, so beta basically is less than 1 and greater than or equal to 0. It's somewhere from 0 to 1. So when beta is 0, what is gamma?
1.
1.
And when beta is just shy of 1, what is gamma?
That's a good question.
It's closer to 0. It gets closer to 0.
What gets closer to 0?
Gamma.
Might want to rethink that. Aaron, I assume you're just plugging in a number really close to 1.
Yeah, I'm just doing like 0.99.
Okay.
I got 7.089. That's rounded.
7.089.
089.
Alright. And if beta is 0.999,
Oh wow, that changes a lot. 70.712.
70.712.
Yes.
So stick it out another 9.
223.
So as beta gets closer to 1, what happens to gamma?
It gets closer to infinity.
Yes.
Okay.
Because as many gets closer to one, my denominator gets closer to zero. And one divided by an incredibly tiny number is a huge number.
Mhm.
Alright. So, I have two numbers here, I'm gonna create a gamma. Because the ratio of length to length here, proper length to length, is gamma. Well, with two numbers, what possible gamma could I have? I'm just gonna come up with a ratio here. Because one of these numbers is LP and the other number is L. Gamma is equal to LP, the proper length divided by the length.
1.1.
Yeah.
Feet, yeah.
Which means that let's see. Alright. So that is gonna be equal to 1 over the square root of 1 minus beta squared. So that's gamma. And so square root of 1 minus beta squared is equal to 1 over 1.1. Just plot these two across the equal sign. And then square it, so 1 minus beta squared is equal to 1 over 1.1 squared. I'm trying to solve for beta. The original question is how fast does it need to travel, so I need to solve for beta. And then bring beta over to the right, my fraction over to the left, so I have 1 minus 1 over 1.1 squared is equal to beta squared. And so beta is the square root.
Got a 0.4166.
Units?
That'd be meters per second, or what, it's feet, isn't it? Feet per second?
Yep.
No. But it's feet though.
Yep.
No.
No, cause that's feet divided by feet.
Oh, so, oh,
So therefore,
It's a ratio.
yeah, it's unitless.
okay.
It's just a number. Alright.
Okay.
But if you're traveling, so you have to travel roughly a little bit under 42% the speed of light in order to fit. However, so if you're sitting there next to the garage watching this car coming at you, that car is traveling near, we'll round off a little bit more, a little less than half the speed of light. But if you're in the car, the garage is coming towards you at about a little under half the speed of light. In one case, the car is shrinking, in the other case, the barn is shrinking, or garage. Sorry, it's a barn later on. So, there's obviously seems to be some sort of conflict here where which one is actually shrinking. And so from one point of view, the barn's shrinking, from the other point of view, the car is shrinking. Or contracting, I guess, this is generally called a length contraction. So we need to do a couple other things before we come back and revisit and talk about how do we actually resolve this idea. So questions on this before we talk about simultaneity. And potentially dash yet one more thought. One more belief. All right. Let's dash another belief.
I'm ready to have my mind blown.
What? Ah, that's the stuff I was looking for. Have to come back to it. Now, if you look at the old tests, most of which you don't have access to because they're for different classes, but they're the characters of Sue and Lou, who were born as conjoined twins. But before, there was Sue and Lou, there was Peggy and Ryan. So, recapture what I had over there, or what I had just erased. All right, so here's the scenario. I have a train car is zipping to the right at some speed v. Sure I get the right people in the right place. I have Peggy on top of the train car. I have Ryan standing off to the side. As the car zips by, when the middle of the train car is even with Ryan, there's going to be two flashes that happen. So there's something that's going to flash here, something's going to flash here. And again, get the right scenario. Meanwhile, inside here, there's a detector.
Really should go through and look at my notes again. Oh, I see what I've done here. Sorry, I have a contradictory note here, but my note was in reference to something below it, not above it. All right.
So if these two flashes go off, if this right light gets to the detector first, so we'll call this R and L, if the right light hits detector first, detector glows green. So these two things go off, the light hits the light from this detector. If it hits it first, this detector will sense that and glow green. If left light hits detector first, or left and right hit at the same time, detector glows red. So Ryan is standing there. He sees these two lights go off at the same time. He knows that the light that shine off will come in and they will hit him at the same time. So from his point of view, they go off at the exact same time. Meanwhile, from the right, this light is now traveling outwards. From the left, this light is traveling this way. But the train is moving in the direction, moving towards the green light. So Ryan says that because this detector is moving towards the right side, it will get the right light first. Do people picture this? So Ryan says, his prediction, green. Meanwhile, Peggy's right there, smack dab in the middle, and from her point of view, she's going, wait a second. If these things are going off at the same time, then, and they're all at rest relative to me, those lights should hit the detector at the exact same time. From Peggy's point of view, if they go off at the same time, they should hit the detector at the same time. Because from her point of view, Ryan's moving, not the train. So Peggy's prediction, they hit at the same time, so it'll go green, or sorry, or red, as you kids today say. So this experiment goes off, these two flash of lights happen, Ryan has his prediction, Peggy has her prediction, then they stop the train after the detector has gone off. And it's only gonna be one color or the other. It's either gonna glow red or it's gonna glow green. The question is, which one will it glow? And then, why is the other person wrong? So let's open it up to questions about what the scenario is, and then we'll get into why one person is right or not. Questions about why Peggy claims that it will glow red.
Yeah, well, if Peggy was in front of the other, boxcar, her prediction would still be red.
Right, as long as she's on the boxcar.
Okay.
As long as she's on the boxcar is at rest relative to her. I tend to put her in the middle for just for aesthetic reasons. All right, so let me recap for Alex. We have a train car that's going by. At this point right here, when there's a detector in the middle of the train car, smack dab in the middle, it's gonna detect a light either coming from the left or right, or both. When the train car is even with Ryan, there's supposed to be these two flashes of light that go off at the exact same time. Somehow something triggers it, these two flashes of light go off. And if the light from the right side hits the detector first, the detector is gonna glow green. It'll stay green. If it gets a hit from the left first, or if the left and right hit at the same time, then the detector will glow red. So from Ryan's point of view, they go up these two lights